All right, we got 1.9, and this one is a nice lesson in the sense that we kind of move away from what we've done in other sections in this chapter, where we have like just a bunch of different topics that we've been doing. Here we just have one. We're talking about functions and their inverse. Most functions have what's called an inverse function. Okay, and what you have on this title slide here is two of them. Right here you see the parent function of a quadratic. Now we'll talk a little bit about this. That inverse technically isn't a function because you'd see it fails the vertical line test, but its inverse equation, if you will, is the square root of x. Okay, if you're wondering, this dashed line right here, that is the line y equals x. And when we're talking about graphs of inverses, it's pretty significant. Okay, so we'll talk about that too. So the focus for this is going to be to start with what are inverse functions, how do we find them, and then how would we identify them on a graph. All right, to start with, and I don't want to kind of get bogged down with the procedure of how to find them or verify them at this point. I just want to talk about them. Okay? Here is kind of the idea. Here are x values, here are y values. Okay, I've made one of these before. It's called a mapping diagram. X values we call the domain, but actually right now I have to, I'm going to have two different functions in this diagram. I need to specify that's the domain for the function f. Our y values, that's the range, again, of f. And here is the function f of x. Okay? The function determines how pairs of numbers get paired together. Okay? If you had a line that was 4x plus 2, again, we think of the function as the how. Take an x value, multiply it by 4, and then add 2. Okay, but it's the multiplying by 4 and adding 2 that determines what the y value is going to be. Okay? Inverse in math can mean a lot of different specific things, and it comes up all the time. It tends to have this common theme that it's related to doing stuff backwards, or it reverses things. Okay? And that is especially true with inverse functions. Draw an arrow going the other way. So we want to take the same two ordered pairs, but we're going to pair them together in reverse order. What used to be x values are now y's, and what used to be y's are now x's. Okay? Over here on this circle, what used to be the range for f, this is now the domain of f inverse. Okay? Those are now kind of like my x values. And then over here, what was the domain for f, that's going to be the range for f inverse. Okay? But the same points are still paired together. They kind of just switch in terms of being an x and a y value. Okay? That's kind of the mindset you should have as you're working with inverse functions, is they take the function that we have, everything just gets reversed and it operates backwards. Here's a good example that I always give students to kind of visualize it. Super, super basic function, okay, that involves hourly wages. You've got a function based on your hourly wage where for your x value, you plug in how many hours you're going to work, and the output tells you, here's what you're going to make, okay? The inverse is going to flip that, okay? The x value would be your wages, and you would plug in a certain amount of money, right? Maybe you're curious to see how many hours am I going to have to put in until I make $1,000 at this job. The inverse function, which again, we'll look at how you would find that, you would plug in an amount of money, that would now be the x value, and then the output would be, here's how many hours you would need to work to make that much. No examples on this slide, it's just a definition, okay? Particularly about verifying inverses. In section 8, we talked a little bit about function composition, okay? How to do it when it comes up. Here's another case where it comes up. If you have two functions and you're going to kind of test them to see are they inverses, you can do it with the composition. You'll just get a very specific answer when you do the composition. The composition of those two will always simplify to x. If it doesn't, the two functions you have that you did the composition with, they're not inverses. If you look back to your notes from section 8, we did a bunch of composite, we did like 3 or 4 of them. We never got x as an answer because on every one of those we had a couple of functions. And we weren't even thinking about inverses when we were doing them, but it turns out none of them were. Let's look at a case, and you should be ready on a test for either one. If I ask you to verify that these functions are inverses or to check to see if they are, they might be, they might not be, right? Depends on how the problem's worded. Okay. These two happen to be inverses. We've seen plenty of examples from the last section of ones that aren't. The order doesn't matter. If you're dealing with two inverse functions, you're going to simplify to x either way. So I'm going to do g of h. So I'm starting with my big old function g, leaving a nice big gap in there where there used to be an x right here, but remember, this is how composition works. H, the whole thing. Okay, again, it's like plugging a function into another function. Five over x plus 2, all of h goes in. Okay? Now make sure on a test, don't just set that equal to x and say, look, they're inverses. I'm expecting to see the intermediate steps. Plus, you got to be on your toes. Maybe I gave you two that aren't inverses, and you shouldn't. They shouldn't simplify to x. First thing that's going to happen is those will cancel. The plus 2 and the minus 2, and I will end up with that. Looks a little funny. 5 over x. I'm going to take that 5 over x, flip it to x over 5, and then multiply. Write that as a single fraction, which would be 5x over 5. The 5's will cancel, and there we go. It simplifies all the way down to x. Okay? G and h are inverses. And again, what that would mean is if you were to plug in an x value into g, it would get paired to a certain y value. The same two numbers are going to get paired together with h, they're just going to be flipped. Your x and your y values are going to switch. Oh, finding an inverse algebraically. Notice the instructions here are a little different, but we actually have to go about this in a very different way because this one didn't give me two functions. And if I'm going to do a composition, I need two. right? I need one function to plug into another, and here I don't have it, all right? So this is a slightly different instruction here to find the inverse. But here's the deal. The procedure to do it really falls in line with the concept of inverses. Think of x and y switching. That's what happens with inverses. So that's what we do. Switch x and y. Okay? Now remember f of x, that's just like y. So when I do that, I will get x equals 5 minus 3y over 2. Now if you're thinking along the lines of functions, that equation just looks, it always just looks odd to me. Right? We're so used to seeing functions solved for y. Right? When they're solved for their y variable, they're in a good form to graph. So we rarely see it like this. And in fact, that's what I want to do next, is I want to return it to its more typical form. So now I'm going to solve for y. In the process of solving, I'm going to get a new function. That new function that I get, it's going to be my inverse. I don't have a lot of room to go down, so I'm going to have to go to the side here. Not a great way to do it, but oh well. I start by multiplying by 2. And I get 5 minus 3y. Oh, I subtract 5, and I get 2x minus 5 equals negative 3y. Oh, I divide by negative 3, and I get negative 2/3 x. Make sure you divide 5, or negative 5 by negative 3 as well. That's been solved for y. But at this point, I would give that function a new name. I'm not going to call it y anymore. This part right here, that is f inverse. Okay? Pairs the same points together as f, but it does it in the opposite manner. Now this whole thing about it doing in the opposite manner, let's get a little bit more specific with that and see how this shows up on a graph. Talked about this just a little bit on the title slide. Okay? The line y equals x has a big role in all this. Now, if you refer back to that title slide, you're going to see something really, really similar here, because these are the two functions that I was dealing with. Except remember, on that title slide, I couldn't call the inverse a function because it failed the vertical line test. Okay? Notice what I did here for my quadratic is I have said x has to be bigger than 0. Okay? Now, I'm going to make a pretty small table because, I don't need it to be huge, largely because it's the parent function for quadratics. I know what that looks like. It's a parabola that's vertex is right at 0, 0. It's one where I just don't need a lot of solution points. We hit 0, 0, 1, 1. And 3, 9. And I start to see like half of it. Okay? That's because of this. I went and cut off the other half. Okay? Here's what would have happened. If I had drawn that in, that function would have failed what's called the horizontal line test. Okay? Now you've heard of the vertical line test before. That checks to see if a graph is a function, like that graph itself. The horizontal line test tests its inverse. Okay? A quadratic, or a parabola like this, it actually fails the horizontal line test. So what I did is I just took out these negative x values. So now this inverse function, it's going to be a function because this quadratic is now going to pass the horizontal line test. Okay, if I drew any horizontal line, it's only going to touch this curve once. Now, once you have a table of values, you know what I really should have done here? Really, I should call that F, because I'm going to make this new table. That's going to be for F inverse. When you have a table of solution points, it's really, really slick to graph an inverse. Okay? Because here's what happens. Those two, nothing. Well, I mean, the same thing actually happened, you just can't tell. This is what the inverse is all about. 2, 4 was a solution point to my quadratic. 4, 2 to my inverse. 9, 3. Remember what I've been saying all along. The same 2 points get paired together, they switch places. What was an x value is now a y value. What was an y value is now an x value. There's 0, 0, 1, 1, 4, 2. And I get what looks like basically half of the square root function. Typically there's solutions that are down here, but remember, because I cut these values out, I didn't get those values down there either. And this whole thing with y equals x, this one is pretty clear to see. It's reflected over the line y equals x. Now, the other thing I like about this example is we have two functions that you're pretty familiar with. That one's a quadratic and the other's a square root. But again, if I wanted to just verify that, okay, take y equals x squared, switch x and y, and you would get that. To undo a square, I have to do a square root, and then you can see in basically just 2 steps that the square root function is indeed the inverse for a quadratic. Alright, I want to do the same thing here, except I hope you're thinking, well, wait a minute. Don't we need a function? And we absolutely do. Here's 2x minus 3. Put together a table of solution points. By plugging in those x values. Now, if you wanted to, you could pause at this point, because what we're going to do on this slide is the exact same as what we did the slide before. Okay, but instead of using the graph y equals x squared, I'm using a line 2x minus 3. Okay, but I'm going to make a table, and then I'm going to make a table for my inverse. I'm going to graph both of them, and then algebraically I'm going to find what that inverse equation is. These numbers are just coming from plugging in the points. I'm going to go ahead and plot them. I'm also plotting a few extra. there's f. Again, this is a great point to switch over and now say, all right, let's get some points to start to build this graph for f inverse, because I can just go through my first table and everything just switches. And we end up with that. There you can see the reflection over y equals x. But the only thing that's left here is I would like to get an equation for f inverse. I'll do that right down here. I'll start with x equals 2y minus 3. So I'm doing this in red because this goes with the graph that's in red, this goes with the table that's in red. We've got a table of solution points, we've got a graph. What equation goes with those two? That's what I'm finding. Okay? I'd add 3 and get x plus 3 equals 2y. I can then actually do it with one step here by dividing by 2. And I could get that y is x plus 3 over 2. And it would be fine if you wrote it that way. At this point I have what I would call f inverse, x plus 3 over 2. It's a line, so if you wanted to put it in more of a traditional slope-intercept form, you could divide by 2. Okay? Just remember this though. You would have 1/2 x, and don't forget that 3, that needs to be divided by 2 as well. It would be 1/2 x plus 3 over 2. Okay? Y-intercept of 3 over 2, slope of 1/2. That's that inverse function that we found on this slide that's all in red.